If you demolish it, you lose the access. Then you have to create the access and then do everything else. It's not an easy task. It's more expensive, basically. It's a fast-flowing river, so scaffolding was 25% of the cost of the whole project, which is nearly £250,000 just for scaffolding. 3 tons label means normal scaffolding doesn't work. It had to be lightweight scaffolding pinned on the edge beam and on the piers. So the piers were used as the beams to put the scaffolding up. That's why it was 250. But that meant that we could keep it away from the floodwater height. Okay. You might see a picture later on where water can come up to the edge. So those are the repair things, and this area was meant to be cut out almost using hydro-demolition, and new steel put in and new concrete poured, because this beam especially had extreme damage on it. At least we thought. Happy enough?
What were the causes of deterioration?
A de-icing salt. We looked at the carbonation depth. It had 1 millimeter carbonation in the last 80 years. 1 millimeter. So it's just completely saturated concrete. And it was purely salt, nothing else, just salt. You can see the logo saying 3 tons. The best part was this bridge was salted along with all the other road network. The salting vehicle is 18 tons. But this bridge was salted. So we asked the client, how could you salt this bridge? It's like, that's normal. So an 18-ton salting vehicle was going up and down on a daily basis on winter, putting salt everywhere. But the label clearly says 3 tons. Those things can happen, So, right. So all of that aside, I'll show you some of the pictures. Excuse some of the images. So this is when the work was on. The display of the work indicates that any form of accident or anything, they know who's in charge and who's where. Oh, it doesn't go like that. Okay. Sorry. So that's the underside where one of the rebar was exposed. We were trying to figure out how to do the repair. This is round bars. Do you use any more round bars? Do you? Okay. We couldn't really get round bars in the UK, so we had to order it in. They still exist, but you kind of have to order it. Yeah, so this is from the top. We needed, remember in the beam design, we need to know if the top does have reinforcement or not. If it doesn't, then the calculation goes away. Oh yeah, the best part. We took cores from the structure and we figured out the strength was 19 MPa. 19. That puts a lot of pressure on us because we were of the opinion up until the previous core tests, which was about 9 different tests, that the average was 33 MPa. It was fine. All the calculations were done. But along with the inspection, we took 8 new cores, including beams and all of it. The strength came back as 19. That was a very stressful day. With 19 MPa, the economics changed because from 33 MPa, that means the bottom reinforcement is sufficient for most cases for taking the flexure. Lower strength means now I have to rely on the top bar to provide the compression capacity to the beam. So I needed now to know that top bars exist, or is it just a fictitious drawing? So the cases where things were critical, we had to dig the top from the surface, figure out the bars. We have no idea of the damage on the bars on the top. Thankfully it's under compression, but still we have no idea. So we needed to dig it out. This is how things can really change, you know. So you can see somewhere that looks very corroded bars. The picture quality is not exceptionally great. So that's one of the that's one of the beams that you're looking at. This is your shear reinforcement. That's your main reinforcement. The extent of damage is quite evident. Hand sort of gives you an idea of how to scale. So what we figured out much later is that these are drill holes trying to get the concrete away, and this is the shear reinforcement, quite damaged heavily. But that meant only the links were damaged, and the main bars in most critical cases were intact, because all the damage was being carried out by the links. So if we managed to get to the links, so this was nearly gone. It was flattened nearly by corrosion. Because the structure was so weak, it was almost uniform corrosion, and that was a blessing. If it was very strong but have smaller weak spots, then things would have been a bit different. Some of the bars, it's not important. There's another structure next to it which has been lasting for 300-400 years, compared to the structure that we're repairing, which is already replaced 80 years ago by a steel structure. So that's the bridge that we're looking at. So these pictures have a meaning. That means the arch bridge is here where I'm taking the picture from. The river bends, which means in flooding it comes with the force, and it goes onto the structure with a significant force. That's how it will look. So the scaffolding underneath it is pinned on the edge beam and also onto the pier stems, so that we have full access underneath it, and nothing much is evident. Everything is aluminum lines so that it's lighter. So the deck was removed, and this is our culprit, which had the sand layer on top of it. So what they did is they removed the concrete block, and then they could just see a sand layer. On top of it they had layers and layers of bitumen. So when bitumen came in, they just poured on top of it. So this kind of loose soil was holding all the moisture, and it was just basically putting the moisture out. That's the expansion joint without having dug out anything. So all we did was remove the tarmac, and the expansion joint was starting to lose concrete even at that stage. It's a full expansion joint. Some of the bars be cleaned and repaired. Some of the bars are nearly sort of gone. You can see the cover there, so that should be the cover, which is millimeters thick. And then the contractor also were required to put sacrificial anodes in the structure. Because the cover was extremely low, we didn't want to take any chances, so wherever we required it, we put a sacrificial anode, and that was electrically connected to the reinforcement by some foam bolting. These anodes exist a lot. Some of the chemicals used. So you can see the grid of anodes. Okay, so there's one anode here. There's one anode here. Every junction it turns, there's one anode. Okay, these anodes were installed closer to the main beam because I'm only protecting the beam. I don't really care much about the slab. See the holes for anodes. This itself is a very destructive process, but have to live with it. So once it's repaired, so you put the anodes here, electrically you connect them, somewhere you will connect them to the steel, so the anodes will corrode for the steel if there's other issues, and then it'll charge the steel from corroding. The repair motor being put back. You can see the anode lines. These lines indicate the anodes being installed. That was the edge, that was one of the transverse beam where the cover was completely gone. That was about 2-3 inches thick. Although it looked really bad, by the time we exposed it, it was only marginal millimeters of stuff gone, because corrosion product is 6.5 times bigger than its volume of metal, so it's really expansive. Anyway, so there were a lot of those. So wherever it sees a tooth saw sort of arrangement, that means we're going to cut all of that, hydro demolish all of that, and then only expose the steel, put the new steel back, pour new concrete in. The new concrete will not do anything structurally, they'll just remain as a good paint, but was needed. I'm looking to see if there's any edge beam. So this is the transverse beam that was so heavily damaged, i.e. in invisible line. This is where the thick rebar, thick cover was falling off. But when you clean it and then this is sprayed with the metal oxide coating to stop it from corroding any further. And you can see that the rebar, the main rebars, are reasonably intact. It's the links that got all the damage, thankfully. That links are easy repaired if you catch on. Yeah, we don't use sand blasting anymore. We use slag blasting. This is slag part. Sand blasting is quite damaging for the people in the. So let me see if there's any more pictures. So that's what you're seeing here is a deck being made below the structure, so you can stand and access and do the repair. And that's what we pay the money for. And what I want to show you is if there's, obviously the client doesn't want to be identified. Yeah, this stuff here, this plastic lining, it's not plastic lining, it's a filter clothing. Part of the requirement of the structure is when you do hydro demolition or when you do slag blasting, none of the debris go into the river. That river has salmon fish. It's a salmon spewing river. You're not allowed to put any output into the river, any. So we had to line the whole thing underneath it, and that's why the cost is high. And the best part was when you go into a structure, 100 meters on either side of the structure becomes your responsibility. And unfortunately that area is infested by what's called Himalayan balsam. It's like a weed. It's a native weed in Himalayas, it's not a native weed there. And it's infected all of that region. So we had to take all of it out, treat the soil, put new soil back in, and put native plants back in. It's all part of the contract. It's weird. I thought we would just do the structure, but no, when you start to do the structure, there's drawings after drawings coming, areas, infected areas to be put back, environmental statements, you need permission from Rivers Agency even to set foot on the land, because you're changing anything. You need to have a meeting with them to convince that you're not changing anything in terms of the water access plan. If you say that you're going to deepen the beam for any chance, it's not going to work. They will not let you do any of that. So yeah, there's a lot I learned from the work. These are the anodes being installed. So that's the aluminium scaffolding put in place. I'm just going to see if there's a picture. So it gives us enough space to sit down and work. These lines are the electric lines to charge the anodes. They're charged by a battery. So these called hybrid anodes, they put the charge on the anodes for a week, and then they take the charge away and then they connect it to the steel. So by polarizing the anodes, hopefully the anodes will work. I still don't know if they work, but I think they do. That's what the manufacturers claim. I have no reason not to believe it. So this is the lightweight concrete poured back into the top deck. They still left the expansion joint with the foam because they were not allowed to close the expansion joint off. we knew things weren't expanding, but we didn't want to take a chance that this can expand because it's now a continuous slab. So yeah, this is nice. What you're seeing here is the bottom bars of the edge beams below and the top bar of the edge beams above. This is the area that we saw as the line damage. So the line was along here, along the walkway. Okay. We exposed it to see whether the shear links, which are these things, whether they were damaged or not. Okay. But when we dug it out, we realized there was a lot of these things, because imagine shear links running for 2 meters in height, and they can flex. So they had ties on the shear links somewhere in between. These were the ties. It was the ties that was corroding. They have no structural meaning other than to keep them. So the edge beam had main reinforcement here, the main reinforcement here, and the shear links were coming down. So shear links were too long, so they had tied them. It was those ties that was corroding, thankfully, because otherwise this would have been a different project altogether. So these are the corrosion spots we were saying. Thankfully they were all on the ties, so we were fine. Yeah, so sorry, how do I turn this? So that's the lower scaffolding as the upper scaffolding. We were working there, but this is just to access this pier. So that's pier with one line and another line here. And water came up to here during construction. We knew that was going to happen. We were expecting that. So yeah, you can see the water rising on the time we were doing some of the work. And that's our typical weather: extreme, stormy, rainy weather. We're now moving into anode-based performance assessment. Okay, so we installed a lot of the anodes, and we wanted to figure out. So a lot of repair was done. We wanted to know if the repair is effective, so we decided to put resistivity pins on the concrete to gauge how effective things were. I'll show you the logic of it, and I'll show you what we did afterwards. But that picture is two of my colleagues. That's Neil from Amphora. He was a student of mine then. They installed the anodes in it, and it's very, very laborious process in getting everything done. Tons and tons of cables have to be put in place. So this is why I was saying that these kind of anodes and these kind of monitoring systems will evolve pretty soon. More of them will become wireless, because these wires are very expensive. They're not nice to be in the structure either. So these are areas that we're working at the moment. The resistance pins at the moment has a wireless ping to it. After he has done that work, he realized how hard it is, so he went and got new stuff. So that's a picture of your lightweight concrete topping, and what you're seeing here as mud and a dark color is light tag. It's a lightweight aerated clay aggregate that gives the concrete a much lighter performance. On top of that, they had PFA, large volume PFA replacement. That's also lighter. And in addition to that, they had no steel. They had what's called basalt rebar. Okay. Basalt is lighter than steel. So they used all of that to get that concrete to be, I think, 1,800, close enough to 1,800 and 900 range. The construction industry is used to steel, and they're switching from steel to basalt. I prefer it to be done on a precast yard, not on site. Performance, they're similar, and the basalt is essentially rock mineral, so they have similar thermal performance as steel, as concrete. So it's good, it's compatible in all of it. But basalt is put together by sand particles, and so you have the basalt fiber, You have the epoxy glue that holds them, and then what they do is they dip it in further epoxy and put sand on the surface to get that grip, which is good. But I have no idea how they change with time. It's only a new technology. But what we found in this structure is the construction techniques will need to be very carefully done. The reason is you take steel. Steel has certain rigidity. Okay, you put a mesh of steel, you put spacers, and then you put the next layer of steel. Again, you put spacers. That's fine. People walk on top of it, right? They walk on top of it. They pour concrete and put all the resources and lines and everything. Basalt need more spacers because they flex. They will be like this. Okay. When people walked on top of it, the bottom and the top reinforcement were together, and they just flexed so much that they were together even when they poured it. We had no access to the site the day that they poured. It was one of those tubes that comes in and pours the whole thing, because the vehicle was not allowed to come into the structure. They had to stay outside. So construction techniques need to be very carefully controlled. Basalt flexes, so you need more spacers, and you need ideally it's precast is better. Cast in situ, you need spacers, you need to control the traffic, and you need to educate the people using it. But it does have benefit. It gives you a lightweight matrix. Corrosion free. That's the biggest advantage here. Not ideal for alkaline environment, so don't put it into factories with caustic soda, that kind of stuff. Because all these fibers rely, and they can be dissolved in alkali, strong alkalis. So if you want to disappear basalt fiber without coating, you can mix it with alkali pH 14, and it'll start to disappear. So if it's in a very strong alkaline environment, don't use it. Probably they will figure out a method of protecting it, but until then, don't use it. So that's the finished structure. There's some nice pictures of it, and some not so nice picture. So the expansion joint remained in place, despite our best effort. The leak was still there after a certain time. We prevented the leak further, so hopefully it's gone. It was coated and finished, so it looks really tidy. And we had installed sensors in it, so we put monitoring box in it. This is the contractor's monitoring box for the anodes, and this is our box for the electrical